All right, today we're going to start trigonometry. And when we talk about trigonometry, what trigonometry is, if you remember back to your fond memories of geometry and even in our trig class, you dealt with a lot of sine, cosine, and tangents. And if you've not taken the trig class here, that's basically all that you remember from your geometry class is when you worked with sine, cosine, and tangent and dealt with the right triangles and Pythagorean theorem a little bit. That's all basically that you dealt with in geometry. We've dealt with all types of functions in the college algebra. We had polynomial functions, we had quadratic functions, we had linear functions. These were all things that we dealt with in college algebra. When we talk about trigonometry, we talk about what is called a periodic function. And when we talk about a periodic function, these are function values or y values. When we talk about function values, we're talking about the y values that will repeat over a certain domain. Periodic functions, things that repeat, continue to go through the exact same pattern or as you go through a specific value or a specific domain. And when we talk about trigonometric functions, the sine, cosine, and tangent, these are periodic functions. Your heart, if you think back to the doctor's shows that you see, and you see a little blip from the heart machine that shows what's going on with your heart, what you see is basically a roller coaster wave with respect to your heart, with respect to expansion, compression, expansion, compression. This is a periodic function, hopefully. Hopefully your heart deals with a periodic function where you expand and then you compress, you expand, you compress, that pumps the blood through your body. And that is a periodic function. When we were in geometry, we talked about the idea of an angle. And when you were dealing with it in geometry, what you learned in geometry was an angle was formed by two rays connected at their endpoints. You had two rays. You had two rays connected at their endpoints. You got Billy Ray, you got Earl Ray. Okay, we have an endpoint here. We continue on indefinitely with respect to the angles. These are two rays connected at their endpoints. And this is what you learned in geometry, and this is what you worked with in geometry. And you did all types of proofs, and you measured these angles. But the thing of it is, in geometry, this angle theta was restricted to our domain. And that domain was between 0 and 180 degrees. And we had the 0 angle, which was the ray right on top of the ray, and then we had 180 degrees, which we called a straight angle, which ended up being just a line. But we were restricted in our domain for this angle of theta between 0 and 180 degrees. Well, when we talk about trigonometry, trigonometry is a little bit different. Because we don't want to just restrict ourselves to the 0 to 180 degrees. When we talk about trigonometry and we talk about an angle is an amount of rotation used to measure the amount of rotation of a ray. used to measure the amount of rotation of a ray. The variables that we will utilize is we will utilize theta, which is a circle with a line through it. We have alpha, and we have beta. These will be the three most commonly used angles, but a lot of Greek symbols are used in regards to angles. You'll see phi, which is a line, a circle with a line through it. But the ones I will typically use will be theta, alpha, and beta. We have to have an initial side. We have to have where we start at. Where we start at, we have an initial side. It is the point at which the angle of rotation starts. Our main emphasis here is we're going to be talking about rotations. Rather than just having two rays connected at their tails, we have an amount of rotation. We have to have a starting spot with respect to a ray. We have a terminal side, which is the ending point for your rotation of the ray. So you have an initial side, which is where the rotation starts, and then you're going to have a terminal side where the rotation ends. We have standard position. When we talk about standard position, and this goes back to geometry or trig a little bit. When we talk about a standard position for an angle, the vertex of the angle is going to be at an origin, because we're going to reflect this, or we're going to take this to an XY axis. We have the vertex of the angle is at the origin, or the end point of the ray is at the origin. The end point of the ray is at the origin. That's a fixed position. And we're going to rotate this ray about that fixed position. The initial side of the angle is going to be on the positive x-axis. Clockwise rotation is negative, and counterclockwise rotation is positive. When we have a negative rotation, we have counterclockwise rotation, this is a positive rotation. When you're clockwise, you are negative. Think about if you're loosening or tightening a bolt, or putting a screw into a piece of wood, lefty-loosey, righty-tighty, okay? When you're going righty-tighty, okay, what's going to happen is you're going to the right and it's going to be going down into the board, or you're going to be tightening the bolt. When you go counterclockwise with that, it's going to lift the bolt out, okay? It's going to be lifting the bolt out, which is going to be a positive rotation here. Okay, if you go into the physics world, you have what is called the right-hand screw method. If you take your hand and you rotate this direction, your thumb will tell you the direction that the screw or the bolt will be going, or the nut will be going. If you go this way, that means the nut's going to be coming out at you. If you go this way, the nut's going to be going inwards, or the screw's going to be going into the board. And that's what this is here, the clockwise and counterclockwise rotation. So if we take a look at an angle, okay, an angle of theta is 140 degrees. We want to draw this angle so we have an initial side on the positive x-axis. Here's your initial side. We're going to rotate this 140 degrees. So if we rotate 140 degrees, this is a positive 140 degrees. So we have to take a look at the idea of this is positive, that means I'm going counterclockwise. Okay, if we take a look at a clock, which is a nice example of an angle rotation, okay, we have the hands of the clock that are fixed at a specific point, and we have rotation of the hands, the second hands, and the minute hands, and the hour hand on the clock. Counterclockwise means we're going counter the opposite direction of what a clock moves. Clockwise means we're going in the direction the actual clock moves. So if you need to take a look at a clock to see which way is counterclockwise, you can take a look at a clock, which is counterclockwise. We're going to rotate this 140 degrees. So we're going to take a ray and we're going to rotate this 140 degrees. Well, if we take a look at the quadrants, which quadrant would this end up in? Jack? Quadrant number 2. Because if we rotate 90 degrees takes us to here, 180 degrees takes us to here. So we're somewhere in quadrant number 2. It does not have to be exact. You don't have to get a protractor out. But 140 degrees means I'm 40 degrees here, I'm 50 degrees here. So it's close enough for government work. This would be our terminal side. And this would be our rotation of 140 degrees. If we go negative 140 degrees, we once again are going to start on the positive x-axis. We're going to fix the end point at the origin, and we're going to rotate negative 140 degrees. Now, if we're going negative, that means we're going clockwise. Which quadrant would we end up in if we go negative 140 degrees, Kylie? Quadrant number 3. Because this would be negative 90, this would be negative 180, so we'd be negative 140 degrees here. (420 degrees), go ahead and do 420 degrees. Which quadrant would you end up in? And draw your terminal side. Check your answer with somebody around you. Lexi, what quadrant do we end up in? Quadrant number 1, where I'm going to go 90, 180, 270, 360. This will take us to 450, so we're going to end up in quadrant number 1. So my rotation would be a whole rotation and then part of another. Okay, so once again, what we're doing is we're talking about rotations. If I go one time around and end up where I started, that's 360 degrees. Okay, we're getting into the winter time here, which lends to give us a little bit slippery surface when driving. Of course, this is very dangerous, so you never want to do that. But sometimes it tends to happen as you come into the parking lot. You put the gas pedal a little bit too much and you start spinning around in your vehicle. Well, the ultimate goal is to do a complete 360, of course. You want to end up the direction you're going. Very dangerous, you should not be doing it. Out there in our parking lot, we have metal triangles around the light poles out there. This is before I came, but the reason why there's metal triangles around those poles is one winter somebody was coming in and they were doing donuts out in the parking lot and they hit the light poles out there and snapped the light pole off. What they had to do to be able to, their punishment was to come in and help dig the holes and to put new light poles in, and then also put the metal triangles around the light poles that are out there. Very dangerous, but damage to your vehicle. But when you go 360 degrees, okay, I use the tomahawk, the dumps, and do the 360 when I used to do that. I wouldn't do the 180 degree dunk. I would do the 360 because 180 was cheap. Okay. Reference angle. Should be a comma in there. It is a positive acute angle formed by the x-axis and the terminal side of an angle. It is a positive acute angle. I guess it could probably be right also. Definition is positive acute angle, but you can have a reference angle that's 90 degrees. It's formed by the terminal side and the x-axis. The terminal side and the x-axis. And the subscript I will use is theta subscript r. So the symbol I will use is theta subscript r. So if we take a look at our theta reference up here, we are looking at the terminal side and the x-axis. Now it doesn't say the positive x-axis, it just says the x-axis. So we have the terminal side and the x-axis. And the angles that we're going to be dealing with respect to reference angles are always going to be positive. So if I take a look at my terminal side and my x-axis, my rotation was 140 degrees. What does the measure of our reference angle have to be here? What's the measure of our reference angle? 40 degrees. Here's our theta reference. So our reference angle is 40 degrees. Go ahead and calculate our theta reference for the next two. And once again, check your answer with somebody around you. What is the measure of the reference angles for the next two? Sean, what do you have for the first reference angle?
40.
40 degrees still. Negative?
No.
All right. Still positive. Because the reference angle is a positive acute angle. So even though my rotation here is negative up to here, you might sit there at, well, it's a negative 40. No, my rotation is still 40 degrees. It's a positive acute angle. Last one. Quentin, what's our last one?
60.
60 degrees is our reference angle because we go 360 degrees takes us to here. So if it's 360 it goes to here, that gives me another 60 more to get to my angle. Old school, in old school mathematics, we have now with our calculator the ability to deal with parts of angles and decimals a lot easier. But the old school way of dealing with some of the mathematics was to do the partials of a degree in minutes and seconds rather than tenths, hundredths, and thousandths. But there are still some areas that deal with degrees and partial degrees in minutes and in seconds. And when I talk about minutes and seconds, you can think about a degree is the same idea as an hour. If I talk about a degree is equal to 60 minutes. And how we symbolize 60 minutes is we put one slash up there. And 1 minute can be broken down into 60 seconds. And what you have with the seconds is a double hash up there. When we talk about minutes and seconds, they are parts of a degree. What we want to be able to do is we want to be able to convert, if I have minutes and seconds into degrees or into decimals, or if I want to have a decimal, I want to convert it into minutes and seconds, I want to be able to go between these two. If I have a pizza that's divvied up into 8 pieces of pizza, I ate 3 of those pieces of pizza. I can say I ate 3/8 of the pizza. But what would be the decimal equivalent to that? How can I make a decimal equivalent to 3/8? Huh? How'd you get that? What'd you do? How did you get 0.375? How'd you calculate it? What'd you do in your head, though? I don't understand. Mathematically, what'd you do? I know you're still out in Hawaii. I get that. You're out there with the surfers and doing that stuff. But you got sunscreen. And I did not hear what you said. If you said it correctly to begin with. 8 divided by 3. Are you sure? See, you got too much sunscreen in your brain there. You're close. You're very close. If you clickety clack 8 divided by 3 in your calculator. There we go. We take 3 and we divide it by 8, and you get what? 0.375. This is the part that we ate. This is the entire quantity. This is the entire quantity. I have 3 divided by the 8. So if I have 41 minutes here, and I want to change 41 minutes into a decimal, 41 minutes is the part of the entire. What can I do with the 41 to convert that into a decimal? Austin, what is it? Divide by 60. So I can take 27 plus the 41 divided by 60 and convert this into a decimal. Grayson, what do you come up with?
27.68.
Point what?
68.
27.68. Well, what can I do if I have minutes and seconds? I can still do the 21 divided by the 60 because that's going to convert my minutes into the seconds. But what can we do with the seconds? I'm sorry, minutes into a decimal. What can we divide by to convert the seconds into a decimal? What could we divide by? Anybody? Yeah.
Divide by 3,600.
Divide by 3,600. Because think about an hour. How many seconds are in an hour? Well, there's 60 minutes in an hour, and then there's 60 seconds within each minute. So I can take the 60 times the 60 or divide by 360, or 3,600. So I have 57 plus 21 divided by 60 plus 18 divided by 3,600. And you can clickety clack that straight into the calculator like that. You don't have to do pieces parts of that. You can clickety clack 57 plus 21 divided by 60 plus 18 divided by 3,600. Sophia, what do you come up with? 57.355. Good with that? Once again, don't be afraid to just put everything into the calculator. Okay? And type it all in. Don't worry about doing things in pieces, parts. Okay? Do entire. Well, what if I had 37 degrees, 37.71 degrees, and I want to convert this into minutes and seconds. I want to go the opposite direction. I want to go the opposite direction. Well, how we came up with a decimal was we divided our decimal, or our 41 divided by 60. We divided our 41 by 60 to get our decimal there. We want to go the opposite in our directions now. We want to go from decimals back into the minutes and seconds. So rather than dividing by, what would be the opposite of doing the division? Lucas? Multiplication. So I can take my 0.71 and multiply by the 60, because we're just putting the process in reverse. And when we take the 0.71 times 60, what do you come up with? Brianna? Shabby? 42.6. That doesn't get rid of all my decimals though. But it tells me that I have 37 degrees and 42 minutes. But we still have this 0.6 of a minute that I need to convert into a second. Well, what can we do with the 0.6 of a minute to convert that into seconds? This is sort of the tricky one here. What can we multiply by to get that into seconds? Courtney? Times 60. So we can take our 0.6 times 60 to give us what? So it gives us 36 seconds. Okay, we will stop there today. What I'm going to ask you to do is just the back side of this worksheet. Tomorrow we'll come in, we'll deal with the idea of radians and the unit circle, which will be the front side of this worksheet. And that will be the back side of your notes. So all I want you to work on today is just the conversions on the back side here. All right, we'll get our brains kicking here again.